We are going to talk about tessellations today. A tessellation, well, they're tilings of shapes. So they occur when a shape, or maybe a combination of shapes, cover a surface without any gaps. There's usually a repetition of shapes. And when we talk about it in our geometry class, we tend to be talking about polygons. So this is an example of a tessellating polygon. We have tessellating rectangles. So it looks like brickwork. So an example of tessellations are brickwork. They could be patios or walls. They can be different shapes than this. You often see tessellations in art, in mosaics. So they are things, if you look for them, you can actually see them. So again, we're going to be talking about polygons that tessellate. Okay, so let's do a little review first. We need to remember how our polygon angle things work. We have different formulas and theorems for that. So if you want to find the sum of the interior angles of a polygon, we use this formula 180 times n minus 2, and that will give us the number of degrees on the inside of a polygon. So I've got a picture of a pentagon here, and so I want the sum of all those interior angles. Now a pentagon, n represents the number of sides or the number of angles, so there's going to be 5. So if I plug that in the formula, it's 180 times 5 minus 2, or 180 times 3. 540 degrees will be the sum of all those interior angles. Now, if you want the sum of the exterior angles, it's a lot simpler. It is always 360 degrees. So I've got a pentagon drawn here, and I've shown where the exterior angles are on this pentagon, but it will be true for any of these polygons. So it could have 8 sides, 10 sides, 100 sides, you name the number of sides, those exterior angles are always going to add up to 360 degrees. And we've proven both of these statements. Interior angles are 180 n minus 2 and exterior are 360 in class, so they've been proven. We do need to remember them. Now, the sum of an interior and exterior angle is 180 degrees. That's another important fact to keep in mind, and that's because they form a linear pair, so they're going to be 180 degrees. So this can be a useful thing, depending on what you're doing. So to continue with our polygon angle review, now if you have regular polygons where all the sides and angles are congruent, that's a regular polygon, we can actually find the measure of interior or exterior angles, one of them. So if I want to find one interior angle, I take the sum of all the angles and I divide by the number of angles I have. So that's 180 n minus 2, which gives us the sum of all the interiors, divide by n, my number of angles. So if I'm looking at my regular pentagon now, it's going to be 180 times 5 minus 2, which is 540. We've already figured that out. But divide by my number of angles, which is 5. So each angle in my regular pentagon will be 108 degrees. If I want to find one exterior angle in a regular polygon, it's going to be 360 degrees, which is the sum of all the angles, divided by n, which is my number of angles. So in this example for the pentagon, it's 360 over 5, which is 72 degrees. The sum of an interior and exterior angle is 180. So I could have, instead of using, say, the interior angle formula, which is slightly complex, it's 180 n minus 2 over n, I could have done something simpler, which is do 360 over n to get the 72 degrees, and then remember that 72 plus my interior angle would be 180, and solve it that way. So it's another way to get an interior angle or an exterior angle, depending how you look at it, using just that exterior angle thing, which is a little bit easier. Okay, so let's look at some examples of what questions might look like if you're working with tessellations. So here's a question that says, what regular polygon tessellates with the regular octagons shown here? So I have a row of these regular octagons, and that word regular is important. It means all those sides and angles are going to be congruent. And I'm basically trying to find, well, what is that angle measure so that I can figure out what polygon would fit in there. And they want regular polygons there as well. So I'm going to use my formula to figure out what is one interior angle. So my n is 8 because these are octagons. So I'm going to use that same 180 n minus 2 over n formula, this time plugging in an 8. And so when I do all that calculation and computation, I get each angle is 135 degrees. So I'm showing, just 2 of the angles that are 135, but of course all those angles are. And why am I focusing on those? Because I want to find that question mark value. I want to find what that is. Now look at that circle that those 3 angles make. The 135, the 135, and now I'm calling that, what was a question mark? I'm making it an X. they're going to add up to 360 because together they make a circle. So since I can see that, I can figure out what x is. So basically, 2 of those 135s plus that x will be 360. Do that computation to solve the equation. The x is 90 degrees. And so once I know that, I can ask the question, what regular polygon has an angle of 90 degrees, right? What regular polygon has interior angles that are 90 degrees? And I think most of us know this without even having to do any computations. Why, that's a square. So the answer to the question is, what regular polygon tessellates with regular octagons? Well, that's going to be a square. Okay, so and I've kind of added another row of these regular octagons, and I can think we can see it a little bit better. Those are going to be squares. So let's look at another kind of question we might get. So another fact that we have is that regular polygons tessellate in a plane if the measure of the interior angle is a factor of 360 degrees, which is a lovely fact. Nobody's going to remember that. So it basically says if you know what an interior angle is, and if you do 360 and divide by that angle measure, if there's no remainder, it divides evenly, it tessellates. What does this mean? Let's look at this question. Do regular pentagons tessellate in a plane? What does that mean? So let's say I've got a regular pentagon here and I'm building my tessellation, so I add in another regular pentagon. So the question I'm basically asking is, well, what fits here and what fits here? Is that also going to be a regular pentagon? If the answer to that question is yes, that means that I can kind of tile together regular pentagons and not get any gaps. The answer is no, then regular pentagons don't tessellate in a plane. You can't just take pentagons and just tile them together and not have gaps. So if you're kind of looking at it, you might say, sure doesn't look like those angles are going to be congruent, the red arrow angles and the interior angles of those pentagons. But looks can be deceiving, which is why we have math. So let's figure out what the interior angles of those pentagons are. And we sort of did this already. We did this a couple of slides back. But basically using that interior angle formula where n is 5, plug everything in, do the calculation, it's 108 degrees. So looking at where x is, and I've got 2 of those 108 degrees around it, 108 plus 108 plus x, is that going to be 360? And I think we can sort of tell it's not, but again, just to kind of show the calculations, it's not. It's 144. And 144 degrees as an interior angle is not a pentagon, right? The answer to this question is no, pentagons don't tessellate in a plane. I would have had to get the same exact measure, which I haven't. So there you go. That's how you would answer that question. But, if you're curious at all, what is that polygon that fits there? What regular polygon will have that interior angle of 144 degrees? What is that polygon? This is less obvious than the previous example where we had 90 degrees, and most of us kind of can remember that 90 degrees are squares. Well, what regular polygons have 144 degrees as their angle measure? There's a couple of ways to approach this. One way is to say, wait a second, we've got that interior angle formula, 180 n minus 2 over n. That gives us one angle. So why don't I just take that formula and set it equal to 144. 180 n minus 2 over n equals 144. Solve it for n, and I'll know how many sides the polygon has, and I can answer that question of what polygon fits there. You could do that. The algebra is a little... it's not difficult, but it's involved, and you might make a mistake. You have to multiply both sides by n and divide by 180 and those kinds of things. So I tend to do these a different way. So the second way, or another way, would be to say, wait a second, if I know the interior angle is 144 degrees, then I can figure out what the exterior angle is. It's 36 degrees. And that's because I know interior and exterior angles of a polygon are linear pairs. They're supplementary, which means they add up to 180. So 144 plus 36, that equals 180. So my exterior angle is 36, and it's easier working with the exterior angles because they always sum to 360. So I'm going to take that 360, I'm going to divide by 36, and I get 10. That means there's 10 sides, or this other thing would be a decagon. Again, these are just a few examples of how tessellations might be worded in questions that you would have to answer. You basically have to be pretty good with your polygon angle theorems and formulas. But other than that, be logical and you shouldn't have any trouble with them. Thank you so much for watching.